Hello everyone, Victor is here, your organic chemistry tutor, and today I'm going to go through this synthesis where we are going to start with cyclopentanol, this molecule on the left, and we are going to make this fun-looking aldehyde on the right. And the first thing that jumps at me right away is that it's not actually the aldehyde that is the focus of this synthesis, but rather the making of this intricate-looking ether in the middle of the molecule. The problem with this ether is that on the left side, that is a secondary carbon. On the right side, we have a tertiary carbon, which means that we cannot use a simple Williamson ether synthesis to make something like that. So that makes our ether synthesis a little bit more problematic because we have to come up with a way that does not follow our general synthetic procedure for ether synthesis. But another thing that I am noticing here is that my ether, let's say this ether is sitting on my carbon number 1, is right next to a carbon number 2, which has a different functional group to it. So whenever we have a situation where we are trying to make the connection to X, and that X is one carbon away from some sort of oxygen-containing functional group, that is most likely a result of an epoxide opening. And depending on how we do the epoxide opening, we can guarantee that our X is going to be either on the more or on the less substituted atom of the epoxide. In this case, atom number 1 is going to be a more substituted atom, so we should do the epoxide opening in the acidic media. But before we go there, let's roll one step back and think about the synthesis of our aldehyde. Normally, we make aldehydes from primary alcohols, and if we have a primary alcohol that looks like that, that will easily make our aldehyde via the oxidation reaction with something that will stop at the formation of aldehyde, let's say something with PCC or maybe Swirn oxidation or something similar to that. That also gives me the exact product that I would get after my epoxide opening, so if my predecessor for my epoxide opening was the actual alcohol that I'm going to draw like this, so I have my pentanol over here like that, then my epoxide would be bringing the rest of that molecule that I have highlighted in my intermediate, meaning that my epoxide would look something like that. And I will highlight here that my carbons 1 and 2 are right over here in my product of the epoxide opening. When it comes to the epoxide reactions, those guys can be a little bit tricky when it comes to predicting the starting material of the epoxide opening, so it's always a good idea to number your atoms and see very clearly where the bond that you are making is going to be. In this case, we are making a bond with the carbon number 1, which means that the rest of the molecule would be my epoxide, and the epoxide opening would happen by breaking a bond between 1 and the oxygen that is sitting on carbon number 2. And since I have successfully reached my cyclopentanol, my starting material over here, that means that I can proceed to the synthetic procedure and fill in the gaps between my steps to actually show what sort of reagents I need to accomplish each of those steps. So step number 1 is going to be the epoxide opening with the acid as a catalyst. It doesn't really matter which acid we are going to be using here, for as long as it is a non-nucleophilic acid, we're going to be just fine. The most common example of non-nucleophilic acid that we are going to see within the scope of a sophomore organic chemistry is going to be something like sulfuric or maybe tazelic acid. And since we are doing the epoxide opening in acidic conditions, we are going to be adding our nucleophile onto the more substituted carbon, giving us the product that looks like this. So if I number my atoms again, carbon number 1 over here, carbon number 2 over here, then my carbon number 1 is on the left side now, and carbon number 2 is on the right side like that. Next, we are going to do the oxidation to convert our primary alcohol into the aldehyde that we need for our final product. For the fun of it, I'm going to be using the Swirn oxidation, which is a two-step process which stops at the formation of the aldehyde. It is important to remember not only the names for your reactions, but also what exactly the reagents are, especially when we are talking about fancier versions of our chemistry. chemistry. So if your instructor is one of those people who like to switch things around from time to time, make sure that you know the names for the reaction and the reagents themselves as well, so you are never caught off guard during the exam. And this oxidation gives us our target molecule as our final product, what we want, our aldehyde here, so we are done. So as you can see, this is a super simple synthesis for as long as you recognize that you need to use an epoxide opening as the key step on this reaction. Could you do it using some other methodology? Well, probably you could, but I doubt that you would be able to find anything that is easier and more straightforward than this type of a reaction where you open the epoxide and then do the oxidation to give you an aldehyde. But if you have some other cool ideas, let me know in the comments below. As always, thank you for watching. If you liked this video and learned something new today, please hit that like button to help promote it and help more students see it. Subscribe to the channel for daily organic chemistry updates. Watch this video next, and I will see you tomorrow.